Good day, everyone. Today's topic is about Turing Machine. So we'll see basically what is a Turing Machine is. So first, we have already seen finite state automata and push-down automata. So we have seen push-down automata is a higher level and more powerful than the finite state automata. So the language accepted by the finite state of machine is going to be a regular language, and the language recognized by the push-down automata is context-free language. Next, we are going to see the more powerful tool than the push-down automata, which is called Turing machine. And the language which is accepted by the Turing machine is called recursively enumerated language. We'll see what is a finite state automata is. So what will be given in a finite state automata is you will have a control unit that reads the input string and try to recognize the given language. And the control moves only in one direction. It can move only from left to right. And it has very limited memory, hence it is very limited in power. So that's the drawback. That is why we are going for push-down automata, which is more powerful than the finite state automata. So what is the difference between the finite state automata and the push-down automata is, in push-down automata, we have a control unit, you will have a set of input terminals, and you will be having a stack. So it can store memory, it can store the input terminal symbols in the stack for its recognition. Here it is considered as a higher class than the regular language. Okay, so the language which is generated by the push-down automata is considered as a higher class. So next we'll see about what is Turing machine is going to be is. So in Turing machine, you can see a Turing machine consists of two things. It consists of a tape. So a tape is it is nothing but a sequence of cells. Each cell can hold at most one symbol or finite number of symbols, and it is holding an infinite sequence of symbols. The tape can have an infinite symbols of sequence. The tape will be accessed using a tape head, so which we consider as a current control unit. So the tape head where it is residing, that will be considered as a current control. And the tape head can move exactly one step to the left or to the right. It can move only in both the directions. It can move in both the directions, but only one cell at a time. Here, as I said, the tape consists of infinite sequence of symbol. So if the input string is over, the remaining spaces will be filled up with a blank symbol or blank spaces. So here the blank spaces will be represented using a blank symbol. So it does not belongs to the terminal symbol. So a blank symbol is not a terminal symbol. So here this blank symbol is used to fill the infinite tape. So the remaining part of the tape will be blank except the input string. So the initial configuration of the tape will be like, suppose if the tape consists of A and B. So this is considered to be as a input string, and the remaining are going to be a blank space. So it will be filled up with the blank symbol. So again here A and B are terminal symbols, where blank is not a terminal symbol, it is a special symbol. So what is a Turing machine? A Turing machine is a mathematical model which is designed by Alan Turing. Because of his name, it was named as Turing machine. So a Turing machine has a finite control. It has a finite control on an input tape. Okay, so that input tape is divided into cells, and a tape head will be scanning one cell at a time. Okay, so it will be scanning one cell at a time. The tape has leftmost cell, but it is a leftmost cell because it's very finite in the leftmost, and it is infinite to the right side of the tape. And each cell of the tape may have hold exactly one of the finite number of tape symbols. So it will have only one tape symbol in its each cell. The input symbol must be a subset of tape symbol. So all the symbols, it should be a subset. So other than tape symbol, we cannot use any other symbol in the tape. And the remaining infinite cells will be holding a blank symbol. So as I said before, the remaining blank spaces will be filled up with a blank symbol to represent that this is an infinite state. So this symbol will be a special tape symbol, but it is not an input symbol. So what will be there in a Turing machine is you will have a control portion. So the control portion is nothing, it's a control over the tape head. So the tape head represents the current control position on the tape. So it is a program and it is deterministic. So for all sort of inputs, you will have a transition. So you will go to either one state or to the other state for each and every input. So that is the major thing. So what is the main use of control portion is, the control portion will tell how a control has to be handled in the Turing machine. So it exactly runs exactly to the form of our algorithm. So if you are given with a problem and you have found out a solution using an algorithm, what are the steps that are to be carried out, that will be taken care by the control portion. Now, what are the following changes will happen in the Turing machine? Suppose if the state changes, so state will be changing from one state to the another state. So this is optionally maybe same as the current state also. So Turing machine, the tape head can move from one cell to another cell. That one cell to another cell movement reading can be a state transition, or it can stay in the same state itself. Then it can print a symbol on the tape where the cell is being scanned. So the current position where the tape head is standing, either it can read or update the cell information, and then the tape head will move either to the left or to the right side according to our algorithm. So what are the operations that can be performed on the Turing machines? It can read a symbol below the tape head. So where the tape head currently resides, that symbol from the tape can be read, or it can be updated. That's your second option. So updated in the sense you can write the symbol below the tape head. Okay, so that will be one more operation. And next thing is, after reading or updating the symbol on the cell, the tape head has to move. So it can move in both the direction, either to the left side or to the right side. So there are set of operations that can be performed in Turing machine. So we have two sets of operations. So let us see the first rule of operation that is performed by the Turing machine. So in each step of computation, when the tape head is currently standing on a particular cell, we can perform either a read operation, or we can perform a write operation, or you can move the tape head either to one cell to the left or to the right. So this is the first set of operations that a Turing machine can do. So on the current position, it can read or it can write or it can perform a move operation one cell at a time to the left or right. Suppose if we are at the starting position, we are on the initial position of the left end, leftmost of the tape, and you are trying to move to the left end of the tape. There is no more moves available. So what happens? So we don't perform any move, we will stay at the same current position. So we will see how transition will be. Is suppose here, now this is a state A and this is state B. So you have a transition from state A to state B. So what is going to happen here is, it is nothing but if you have a production rule A tends to B comma R, so which can be written as A or B slash R. So what is the first thing is, the first A which represents the symbol to be read. So it is the input symbol which is read in the input string. And second thing is the symbol that is to be written on the tape. Okay, so the symbol read on the tape and the symbol that is to be written on the tape, which is given as A and B. And after performing read and write operation, the tape head has to be moved to the either left side or to the right side. So here I am performing my head direction to move to right direction. So here it is moved to the right direction. Suppose if I don't want to update the cell, I don't want to update it, I want to leave it as the same. So you will just write the same symbol again on the same cell. Suppose you have a symbol tape like this. and you have A and your tape head is here. So when you are performing the first production rule, this A will be replaced by B. So it will be replaced by B. Suppose I don't want to update any cell. So if I want to the same thing means, so you will rewrite the same symbol again. So how do I write it? So I will read A. So this will be read A, and again I am writing the same A, and then I am moving my tape head to the one cell right side. So again this is a transition from A to B. Now what will be the next set of operation you will have is, the second set of operation is, the control is similar to the sort of finite state or a mission. Okay, so it's a similar to your finite state mission. So here you will have the same initial state, like where the function, the control unit has to start from, and you will have final states. Here there are two types of final states are there. One is an accept state and another one is a reject state. If the string is accepted, then it will enter into the accept state. Suppose if the string is not matched with the language which it is generated, so it will enter into a reject state. So in Turing machine you will have two final state. One is accept state and another one is a reject state. Then again, sometimes the commutation may come to either one of the case. Either it can come to accept state or it can enter into an infinite loop. So there are three types of things are there. One is halt and accept. So partially the string is being accepted without seeing what is the rest of the tape is consisting of. So it will halt up to that position my string is accepted. The second case is in the middle of the scanning itself. You may understand that the string which is read is not in the form of language. Then we can stop it and we can reject the string. Sometimes a machine may fail to halt. That means it may enter into an infinite loop without some proper rules. So these are the three conditions that can happen when a commutation come to a halt or a looping process. Right, coming to the formal definition of Turing machine. Here, Turing machine is represented using 7 tuples. So it is represented with Q, which is nothing but a set of finite states or finite set of states, and sigma is nothing but the finite set of input symbols, okay, or terminals, and the lambda is going to be the tape symbols or tape alphabets, a set of tape alphabets it holds, and tau is nothing but the transition function, so which is defined as a number of states into the tape symbol which can produce, implies the tape symbol with left or right direction along with the state. So you will be having from A to B means it will be with the state with a input symbol. Simple, if you have a state A and I have a transition to B for the symbol 0 and 1 should be written and I have to move left direction, then you will write the tau function as tau A comma 0, which will be equal to B comma 1 comma L. So here A and B are states, 0 and 1 is the terminal symbols, and L will be the direction where the tape head has to be moved. And next one is Q0, which is the initial state for the Turing machine, which is similar to your finite state automata. And B is the blank symbol. So what is the blank symbol we'll be using? So that is represented by B, and F is the set of finite states. So it will be accept state or reject state. So how do you write a production rule in the Turing machine? So as I said before, if you are having a Turing function like this, you will write the Turing function as tau A comma 0 implies B comma 1 comma L. So this is how you will write it. So here 0 and 1 is going to be the 0 is the input symbol and 1 is the tape symbol. Okay, so the symbol that is to be written on the tape, and L is going to be the direction. So here I have written it as tau Q0 of A implies Q1Y, or where A is an input symbol, Y is a right symbol on the tape, and R is the head movement towards the right direction. Now what is Turing thesis is? So the Turing thesis states that any computation that can be carried out by mechanical means that can be performed by some Turing machine. So if you are able to perform any problem, if it is solved by any mechanical problem, means if you are solved using an algorithm, that can be performed using Turing machine. So there are few arguments that support this Turing thesis. So the first argument is anything that can be done on an existing digital computer can also be performed in Turing machine. So whatever you are trying to do in a computer, that can be also performed in the Turing machine. And one more thing is, and no one has yet able to suggest a problem solvable by what we consider an algorithm for which the Turing machine program cannot be written. So there is no program is ever written that a Turing machine cannot perform. That means Turing machine can perform all sort of problems which has an algorithm. If a problem is solved using a finite number of steps, then that problem can be solved or performed on a Turing machine. So these are the two arguments that supports the Turing thesis. So anything if you are able to solve in a finite number of steps, that can be performed by the Turing machine. So what is the language that is accepted by the Turing machine? So here the language that is accepted by the Turing machine is called recursively enumerable language. Okay, so if a language L with a set of input terminals which is recursively enumerable, if there exists a Turing machine that accepts it. There are other types of languages also there which we will come across in upcoming topics, like Turing recognizable language, Turing decidable language, and the language that is not recognized or decidable by the Turing machines. So let us see an example for a Turing machine. We will come to an understanding how Turing machine works. So let us see an example. So the problem is design a Turing machine which recognize the language L is equal to 0, 1 star 0. So what do you mean by this? It should start with 0 and it should end with 0, and intermediate it should consist of only ones. So it can be either 0 or 1 or more. So the language that is going to be generated is, it can be either 0, 1, 0 or 0, 1, 1, 0 or 0, 1, 1, 1, 0, or it goes on like this. So the starting and ending should be done. So as I said before, we are going to use a Turing machine. So we have to recognize the string. So what we are going to do here is, we have to design an algorithm. So let us consider an input string 0, 1, 1, 0. So after seeing first 0, we should go to the next input string that is to be read on the tape. So you have to move 1 to the right direction. So when 1 is written, so what I will do is, after reading 0, I will replace the 0 with some terminal symbols. Either I will take it as X. So if it is 0, then X. Then after X, if we are encountering 1, then it should be Y. Again 1 means it should be Y. Then when you come to the next 0, it should be X. After this, if you have any 1 or something like that, then it should go to a reject state. If you don't have 1, then it should be accepted. So how to define this? We will start doing with the transition function. So first we will draw a transition diagram. From that we will understand how to create the table. Okay, so let us start with an example. So now this is the tape. Okay, so the current input symbol is 0. So what I'm going to do here is, as I said before, I will replace zeros and ones with some variable. Okay, so that we will come to a conclusion how it is done. So first, when you read 0, I'm going to write in the tape. So the current control of the tape will be in the first cell. So I will write it as X and make the tape cell to move to the next cell. So what happens? You will have the next cell is X, and you will have over here. Now you will be here, and the next input string should be read over here. So what I do here is, now I write this into a transition. So when I read the first 0, so I have to replace it with X, and I have to move to the right direction. So 0, I will write X, and I will move to the right side. So this will be Q1. So we'll see the rest of the things afterwards one by one. Okay, so if I'm going so I'm going for the accept state. So now it is 1, so I will try to write it as y, and I will again move to the next cell. Okay, so now your head will be in the next cell. Now the next input symbol is y. So what happens, we have come to q1, right? So what I go is, if one is coming, so let me have, if another one comes, I can stay in the same state, so I don't want to go anywhere. So I'll put an infinite loop, 1 y, I'll go to right side, so I'm going y. So when you come for the next one, again I will stay in the same state itself, so I don't want to go to any other state, because if you go, because until all 1 is to be done, you can see this is one stage and this is one stage, so this is where we have to check. So after 0 you may have multiple ones, so until then you can stay in the same state itself. So I'm staying in the same state 1 and writing y and moving to the right side. So now I will write y. I have come to the next symbol. So next cell I have come over here. The next input is 0. Okay, so the next input is 0. Now you are going to see a new symbol. It's not 1, it is going to be 0. So what I'm going to is, from Q1 I'm going to Q2, next state. So which will be 0, and I will write x and I will go to the right side. So 0, x and right. So now I have come to the end of the string. So, and I have to have a blank symbol. So you will be having a blank symbol after this state. So if it is going to be a blank state, I will write like, if it is blank, then write the blank state and move to right side and give it as Q3. So Q3 is your accepting state. So this is your accepting state. So as I said before, a Turing machine is a deterministic. So you have to tell what is the other states, where what is the other operations that will be performed. Okay. Now if you see, if it is 0, it is moving towards the accepting state. Suppose if we are starting with the string with 1, then it should enter into a negative state. So I will write it like, so I will put a Q4. Okay, I'll erase this. So I just 1 second, I'll change the color. So I will take it as Q4. So this is a rejecting state, right? So if it is 0, you will go for towards the accepting state. If it is 1, so I will write 1 and I will go to the right side and I will say the string is not accepted. So if the starting symbol is 1, I will enter into a rejecting state. Similarly, you can see the language is 0, 1 star. So that means there is no empty string should be accepted. So I will have an empty string and an empty string to be written and drawn. So if you have an empty string, that will also go into a rejection state. So now you can see, if it is 0 or 1 terminal symbol, you have 2 states, and other possibility is for blank symbol. Now coming to Q1. Okay, so after reading 0, if you are consecutively reading 1, and if you are going to 0 means you will be going on. So after reading consecutive ones, if you have a blank space, for example, it is just 0, 1, 1 alone. So after reading 0 and several ones, if you are encountering a blank space, means then that should be also not accepted. So you have to go for a rejecting state. So I will write a blank symbol and go to the right side. So that will also enter into the rejection state. So this will be also an rejection state. Now after, let me come for another case. Now up to this case we have done. Now coming to the Q2. So after reading 1, 1, 0, if I have another 1 or if I have another 0, for example, this string is read, and the last thing is, if it is again a 1 or 0, then it should be also not considered, because the ending must be with a single 0. So multiple zeros, or after 0, if another 1 comes also, it has to be rejected. So I will put, if it is 0 or 0 of right and 1 of 1 or right, I should go to the rejecting state. Okay, so I will be rejecting the state. So from this, what we understand is, so it's very easy that we don't need full power of the Turing machine to understand this language in order to show that the Turing machine works, how it works or something like that. So we have used only part of this. The second thing is it is deterministic. We have to write for each and every symbol. Okay, so you have to write it for each and every symbol. Suppose in future, if you are drawing a transition diagram without writing for all the terminal symbols, means so the diagram which is drawn for the terminal symbols, that are only for the accepting state. So if you don't have a transition for another symbol, if it is by default, we will consider that it is going for a negative state. Suppose in this diagram, if you see what are the things that I have drawn in the red color, if I am not mentioning it, then for example, when you are going with Q0 and I am starting with the input string 1, means there is no transition, means then it means that it is going to a halt position and it is rejected by default. So this is the Turing machine's possibilities. Okay, so this I have shown it as a simple example. So you can see the language which is given is not a regular language, but by Turing machine it is very powerful. It can recognize this language using a transition diagram. So we'll see in another example how a Turing machine is designed for the language A star. So what will be the language that will be generated is you will have a multiple A's. So we'll start with the transition diagram again. So I will draw the transition diagram. So we'll start with the initial state Q0. Okay, so this is your initial state. So when you have first input symbol as A, okay, so you will write that. So we don't want to go back and here and forth. If it is A, you have to go for the next step. So I will write, I don't want to write it as any other symbol. So I will write A itself and I will move to the right. So now I am moving to Q1. So if you have multiple A's, again I will stay in the same state. So I don't want that. So A, R, comma, R. And finally, after all the A has been read, if you are encountering with a blank space, okay, so let me take it as a blank space. You will write the blank space and write, then you will say my string is accepted. So this is the accepting state. So that's all for the acceptance for the language. Okay, so this is accepting it. So you can see here I didn't write any other option for rejection state. So if other than any other symbol it comes, it is directly goes into the rejection state. So let us write the definitions for the Turing machine. So what will be the set of finite states you have? You have Q0, Q1 and Q2. Now what are the terminal symbols we have used here? It's only A alone we have used here. What are the tape symbols we have used? Lambda. So I have used A and the blank symbol. So it's a blank symbol. So here this is a blank symbol we have used. Okay. So you can use either B or you can use anything. So when you are using a terminal symbol like A, B, C, D, if you use a blank symbol like this term, it will be very easier to understand, right? Now we are going to write the transition function. So we have B. Okay, so we'll write other things first, then finally we'll write. So your Q0 will be Q0 and your B will be a blank symbol and F will be Q2. So it's your final accepting state. Okay, then what is your transition, right? So now I will rub this blank symbol. Now the transition functions. So tau for the input Q0 with the input string A, I will be going to Q1 with the same input A to the right direction. So simple, input symbol, return symbol, direction. So return symbol will come in the right hand side and input symbol will come in left hand side with the tau function. Similarly, we have another one. So Q1 A, you will stay in the same state Q1 and you will write A and you will have a right direction. Then finally, when you are in Q1 and if you have a blank space, then you will go to Q2 with the blank space written and to the right. Okay, so that's all the transition function. We don't have any other transition function. So this is how we have designed a Turing machine for the given language A star. Now let us see the last example for the Turing machine. So I am going to design a Turing machine for the language L is equal to 0 power n, 1 power n, where n is greater than or equal to 0. So what does the language L says about? So if you have n number of zeros, then the same number of ones should be available in your language. For example, so if consider L, so it can be epsilon because n can be equal to 0. It can be 0, 1, 0, 0, 1, 1. It can be 0, 0, 1, 1, and it goes on. So this is the language. So first you have to design an algorithm how to record that we have equal number of zeros and equal number of ones. So let me write an algorithm for this. So before algorithm, let me see an example. We'll see an example how we can do this. So 0, 0, 0, 1, 1, 1. So how do we check this? For each and every 0, there should be a 1 that exists in the language. So what I do is, when tape head reads the first symbol, it will become X. After that, it will avoid, it reads towards the right side to see the leftmost one. So it will try to find the first one in the leftmost occurrence. So when it goes to 1, it will make it as Y. After that, it will move towards the left side of the tape until it encounters the next leftmost 0. For example, I will write it in a step-by-step process so you will be able to understand. So when you have 0, it will be made X 0, 0, 1, 1, 1. Now the tape head move towards the first occurrence of 1. So when it encodes the first occurrence, so it will be X 0, 0, Y 1, 1. Now the head will start moving towards the left end of the tape to find the next leftmost 0. So that is the next leftmost 0 is this. So what happens is this will become X 0, Y 1, 1. So okay. Now after making this, again it start towards the next leftmost 1. So when it encounters this one, it will be made Y. So you will have X, Y, 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 1. From here again it will move towards this 0 and finally X, 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 then Y, Y, 1. So it moves towards the 1 and the final 1 will become Y. After that it moves towards the blank space, then string will become accepted. So this is how we are going to do. So we are going to form an algorithm for this. So first thing is, the step 1 is change 0 to X. So the terminal symbol 0 should be made into X. Then move the tape head to the right side to leftmost 1. Okay, so the leftmost 1. So leftmost 1 means the first occurrence of 1. Okay, so if in this step, if none is available, that is if there is no 1 is available, then we will go for a, then we will go for, if no 1 is available, I will take no 1 is available, then we will reject the string. Okay, otherwise we will go for change the 1 to Y. Now fourth step is, we will move the tape head towards left direction to the leftmost 0. Okay, so we will move to the leftmost 0. So you can see here, after making Y, it will move towards the left direction to find the leftmost 0. So that is, this is the leftmost 0 you have. Okay, so repeat step 1 to 4 until all zeros and ones are done. Okay, and the last step is, so I'll write it over here, is the 6th step. So move to the right. Okay, we'll move to the right and you find no more ones. So after fifth step is repeated, and after I am moving towards the right side, I don't find any ones. Okay, if I don't find any more ones remaining, I will enter into the acceptance stage. So I will accept the stage. Okay, so this is the step. So what I do, leftmost I will take it as 0. Leftmost 0 will be made as x. Then I start moving towards right. I see first 1, I make it y, then again I move towards left. When I see 0, again I make x. So like zigzag, we are going to perform this. Right, so first we will draw the transition diagram. Okay, so we know it is going to be q0 my initial state. Okay, the q0 will be my initial state. So you can see the first step is, if you have 0, you have to change it into x. So what I will do is, I will transition from q1 to q0 to q1. So what is the thing is, so I will write it in another color. So it is, if it is 0, okay, sorry, one second. If it is 0, change it to x and move to the right side. So you will be moving it to the right side. Right now, if you are encountering another 0, so for example, so I will take it as an example, 0 0 0 1 1 1. So when this 0 is done, it is made x, I am moving to the next state. So now your control will be here 0 0 1 1 1. So if I encounter multiple zeros, until 1 there is no change. Until 0, so you have to be just traveling towards the right direction. So what I do is, so I will write it as 0, I will have no change, and I will move to the right direction. So what happens from here, it will not change, it comes to the 1. When it encounters 1, I am going to the new state q2 with the input 1, and I am replacing it y, and after replacing it I have to travel towards the left side of the tape, so I will give left. So up to this you will be clear. I will write it similarly. So I will write like this. So initially q0, so q0 and 0 will take care. So what happens is, it will write it as x, and q0 will move to the right side. So now you will have 0 0 1 1 1. Now this q0 and 0, sorry, it will come to q1. Okay, so now it will become q1. Now q1 0, then what is the direction? It has to be no change, only right side movement. So you will have 0 q1, again 0 1 1 1. Again q1 0 means q1 0 0 q1 1 1 1 1. Now this is the turn, and now this is the step. Now in this step, what I am telling, if it is 1, you have to replace it as q2. So you will have 0 0 q2 y. Okay, q2 y 1 1. Why it is moving still in y2? Because after replacing 1, after updating 1 as y, it starts moving towards left side. Now it is in the left side. Now you have to see in this direction. Okay, now this is the direction we have been going. Now in this direction, now these two variables q2 and 0. So what I have to 0, I have to be in the same state. I repeat, I will stay in the same state. So if it is 0, I will write 0 and I will move towards my left. So what happens? X 0 q2 0 y 1 1. Okay, again 0, so it will have q2 0 0 y 1 1. Now if it is x also, right, I can do that. If it is x, I will move towards the right. So what I am doing is, now from q2 I have to tell where it has to belong. So what I do is, again I have to replace it as x. So what I do here is, I am going to take it in this fashion. When you come to this state, again x to be written. Now what is the state has to do is, the same process what we have done recursively in the first step, that has to be repeated. That is, it has to replace 0 should be replaced as x. So what I do is, I take this transition to q0. So for what is the input I am taking, if it is x, I'll write it as x, and I'll start moving towards right direction. Now what happens? This x again written as x, and moving to right, it will become q0. Now q0 0 0 y 1 1. Now this is q0 0 0. So what happens? It will replace it as xx, and it will become q1 0. because that's the term I have given over here, right? So it goes on, it repeats, and it goes and comes and goes and comes. Now you have to consider, now q1 is 0. So q1, now I will write it over here. So now xx 0 q1, okay, y 1 1. Now what is for y? There is no term I have given for y here. So if it is y also, there is nothing to be done. I have to move towards the right. So what happens is, so I will write it as y. I will write same y and I will go to the right direction. So it will be 0 right, y right. So what happens? xx 0 y q1 1. Now q1 state with input 1, what is to be done? It should be replaced as y and move towards the left direction. So xx 0 q1 y. Oh, one second. Okay, so it's y q2 y1. Now q2 should be moving towards this 0. Okay, it has to move. So you can see, if it is x, it moves to the right. If it is 0, it moves to the left. But here it is y. So if it is y also, it should move towards left. So y is written as y itself and moving towards left. So what happens? Now you will have q2 here, y1, 0, x, x. Again, if it is 0, x will come to this part. Then it will change to q1. Again, the process will be repeated. Okay. So this is the process. It is done. Now we'll rub all these things. Right. Now you see the final one has become y. Now q2 move towards the leftmost for finding 0. So what happens is, you will have y q2 y, then q2 y. Now q2 with the input of x towards the left direction. So what happens? It will come to q0. Now q0 y. Now you see q0 is here. Only for the input 0 I have done, but not for the y. So what, from this you can very clearly see that you have equal number of zeros and equal number of 1. So when q0 encounters with the input y, it returns y and go to the right side, and it says that it is how many y's are there. So until all the y's is done, it moves towards the right direction. So we'll take it as this one as q3. So what happens? You can see here, this I will update here itself. So what happens? q0 will become y q3. Then if it q3 is encountering again and again y, again y and y go to the right side. So y, you will have q3. Then finally you will have y q3. Now you will encounter with a blank space. Now if you are encountering with the blank space towards the right, we will enter into the accepting state q4. So now I will take my q4 is my acceptance state. So now this is the transition diagram for the given language 0 power n. So we will see what is the definition for Turing machine. So from the transition diagram, we will define the Turing machine. So m is equal to q comma lambda sigma comma lambda. Okay, sorry, it's a lambda comma tau q0 blank symbol b and the final state f. So what is q? Q will be q0, q1, q2, q3 and q4. Right. What will be sigma is, sigma will be either 0 or 1 alone. What is the tape symbols you can have? You can have 0, 1 and the lambda symbol, that is the blank space symbol. Right, transition function, we'll write it last. So we'll have q0. So I'll write q0 here. So q0 is going to be q0. F is going to be your final state, that is q4. And your b is going to be lambda, some symbol. Now we'll write the transition function. So we'll start writing from one by one. So tau, I'm going to write. So first thing from the initial state. So q0 comma 0, I will be going to q1 with x comma r. So that is the state, right? So now from q1, for the input 0, I stay in the same state q1 with the 0 and moving towards right. Then tau q1 of y, symbol for y, I will stay still in the same set 1 and write y and I will draw. Now if tau q0 1, so I'm talking about this one. So if it is for the input 1, I will be going to state q2 with writing of y towards the direction left. Now coming to the state q2, I have three transition functions here. So first write the self transitions alone first. So q2 for the input 0, it will stay in the same state 0 and move towards the left direction. q2 with the tape symbol y, you can have, so you will be having the tape symbol. So one second. So it will be q2 y moving towards left. Now if it is with the input x, then it should go to q0 with x and moving towards right. Okay, you will be moving towards the right side of the process. Now next thing is, I have finished with q0. Still q0 with y is going to y of y. Okay, 0. I have two transitions for q0. I didn't write that, so let me write that q0 transition again. q0 comma y for input y. So you will have going to q3 with y with the r direction. Now for q3 with the y, you will stay in q3 itself with y for r. Okay, and finally if q3 is encountering a blank space, then I will go to q4 with the blank space with right direction. So you can check how many rules I have written. So you can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you have 3, 6, 9, 10. So 10 transition is written. So this is your finite state automata. So let us see how with the finite state automata the input string is accepted. I will give an example. So we have designed the Turing machine. So we have designed with the transition diagram with the language that is accepted by the Turing machine. Now we will check whether an input string is accepted by the Turing machine or not with the transition function. So this is the function input string which we are going to consider. So we will be starting with q0. So I will write like this. So q0 0 0 1 1. So this gives, so q0 0. So what happens? Q0 0, it should be made as x. So x q1 0 1 1. Now this again will be given as, right now it is moving in the right direction. So you will see q1 and 0. So what is q1 0? Q1 0, nothing, you have to change. So you will have x 0 q1 1 1. Now if it is q1 1 1, this role will be taken care. So you have to change it as y and start moving towards left. So x 0 q2 y 1. So it will be replaced into y and it has to move to the left direction. So now it is q2. Now it is started moving here. So you q2 of 0. So moving towards left direction. So if it is q2 of 0, q2 0 y1. Now if q2 of x, it has to be changed to x0. So x will be written and it will become q0 0 y1. Right, you can see here, this is the rule. q2 of x, go to the state q0 x and move to the right side direction. Now it will be start moving towards right side direction. So now it will become xx q1 y1. So q1 of y1 again move towards the right direction only. So you will have xx xx y q1 1. So now it is in this direction. So q1 of 1, you will make it as y and move towards left. So I will write like this. So it will write xx y q2 y. Now it is started moving in the left direction. So it still stays in q2 until it encounters x. So xx q2 yy. Now in this direction it becomes xx q0 yy. Now it start moving towards right direction. Now q0 and y you can see Q0 and Y is going to Q3. So you will have XX, Y, Q3, Y. Still it's in the right direction. So it gives XX, Y, Y, Q3. Now Q3 has come to the end of the tape. That is, the blank space is encountered. When Q3 is encountered, you can see XX, Y, Y, Q4. So it is in accepting state. Q4 is your final state. So this is how your Turing machine is designed for the given language. So hope I have discussed all the formal definition and introduction to the Turing machine. So we have seen examples for Turing machine. Hope we will meet with a new topic in the next session. Thank you.